Hi everybody. I'm going to work through the triangle problem, which is problem 1 on the center of mass practice. Alright, so you can see here that I have a triangle, and it may not be a perfect equilateral triangle, but I tried to draw my best here. So the problem states that you have an equilateral triangle with 5 centimeters per side, and it's rotating at 120 revolutions per minute. First says draw a picture. I've got a picture here, and determine the center of mass. So let's think this through here. Where would the center of mass? You could pretend this. Was a wire shaped into a triangle, or you could pretend it was, a piece of metal shaped into a triangle. I don't think it would really matter in terms of center of mass. So let's pretend it's a, let's say it's a wire in terms of center of mass. So let's do a little thought experiment here. So it might be tempting to think that the center of mass would just sort of be like halfway up this line here. But we're going to see in a second that that's not true. The center of mass can't really be halfway up this line for this reason. So let's draw, like, let's say halfway is, right about there. So let's do a line across. If you look at this, left to right, there is as much mass on the left of my vertical line here as there is on the right. So the center mass must lie along this midline, but it can't lie along this line. And the reason is there's more mass below the line than there is above the line. You can see I can have two chunks here and here of material. Then down here I have 1, 2, 3, 4, roughly. Oh, my pen turned off. 4 chunks of roughly the same size. So there's more material on the bottom, so that can't be the center of mass. Oops. Alright, sorry about that. I erased my triangle. So let's get rid of these little circles here. Get rid of that. So the symmetry argument works for up and down right now. Now you could also make that same argument by starting a line right here and drawing it to the midpoint of this side here. If you had just tilted the triangle, so the center of mass must lie along that line. Let me just get rid of some of these little marks here. Alright, so let's draw that line in. I'm just going to turn my screen. Okay, something roughly like that. And you could also make the same argument that if you just tilted the triangle from here to here, both sides of that line would have the same amount of matter. So it looks like the center of mass is going to fall right in here where all of those meet. Alright, the next step is to try and figure out how fast this thing is rotating, and it asks us just to look at one of these tips here. If this really were rotating, each of these little tips would sort of sweep out a circle. And how fast the tip is rotating depends on the radius of that circle. You should recall that the tangential velocity is the radius times the angular velocity. So before we can figure out this, we're going to need to know this. And this we can calculate based on the 120 RPMs that they gave us. So let's start by I guess working out what that is. 120 revolutions per minute for every 1 minute. And I want to get rid of revolutions. So for 1 revolution you have 2 pi radians. And I want to get rid of minutes, so I'll put minutes on top. For 1 minute you have 60 seconds, and let's see, that's 240 pi over 60, and the minutes go away, and the revolutions go away, and I'm left with radians per second. Alright, so I can get rid of that, and just reduce this. So this I will use in a little bit here for the angular velocity. The radius. Well, I've got some information. They tell me that this side here is 5 centimeters. So what else can I do here? That means this is 2.5. And what else do I know? I know this whole angle here has to be 60, but we've cut it in half, so that means this little one is 30. And now I can use this little triangle here and figure out this little side, which is what I really want, because that's how far away each tip is from the pivot point. So I'll just redraw that little triangle. You've got a 30-degree angle, you've got 2.5 centimeters on this side, and so I'm going to use cosine is equal to the adjacent side over the hypotenuse, which is really r, and then we'll just solve for r. So when you punch that into your calculator, you get about 2.89 centimeters, or if you simplified it, that's 0.0289 meters. So if we were watching this tip here as this object was spinning, then it would sort of sweep out a circle as the object rotated. And now I can just take this right here and this up here and plug them into my equation. And we've got 0.0289 meters times 4 pi radians per second. And I just plugged that into my calculator, and I got 0.36 meters per second. Now the last question was, if the angular velocity of the triangle is constant, what's the net torque acting on the triangle? Well, we know that if the angular velocity is constant, the net torque must be 0. Alright, hope that helped everybody.